It's Rust in Production, a podcast about companies who use Rust to shape the future of infrastructure. My name is Matthias Endler from Corrode, and today we talk to Sebastian Scholz from Gama Space about controlling solar sails and satellites with Rust. Sebastian, thanks very much for taking the time for the interview today. Can you say a few words about yourself and about Gama?
Yes, thank you very much for having me, Matthias. I'm very excited to be here. My name is Sebastian Scholz, and I'm an electronics and embedded system engineer at Gama Space. We are based in Paris, and I've been with Gama Space since January 2023. Our mission, our Gama Space's mission is to develop and provide a propulsion technology called solar sails in space. And to do that, we are using Rust in various places, and that's what I'm here to talk about.
Now, not everyone might be familiar what a solar sail is. Can you describe the principle behind it?
Yes. So the concept is actually rather simple. You know, when you have a sail on a boat, you have the wind blowing into it. In space, you don't have that, but you have the sun. And the photons of the sun provide some amount of pressure on a sail. So if you have reflective space, the reflections of the photon give you an impulse and so provide momentum to your sail. So basically, it's a way of moving in space, but without fuel and just relying on the sun.
Basically, free propulsion.
Basically, free propulsion. That's exactly it. The main advantage of it over combustion propulsion is that you don't need to bring your fuel with you. So as you might know, it's still kind of hard to get mass into space. So by saving all of this potential fuel mass, it's going to be easier and cheaper to go into space.
And the trade-off is speed, I'm assuming, right?
Yes, of course, there are some downsides. Compared to a normal combustion engine, the specific impulse that you get is rather low. So that means the acceleration is extremely low, actually, in the area of a few newtons versus kilonewtons that you get from normal propulsion. So that means you have to plan your trajectories accordingly. But, I mean, the benefit is that this propulsion is infinite compared to the fuel, because at some point fuel runs out, but the sun, it's going to take a very long time for it to run out.
Unless you're too far away from the sun.
Even if you're too far away from the sun, you still get some amount of propulsion. I mean, it's not like you're on an empty tank. You still have some amount of movability, even if the sun is very low. But if you're on the outside of the solar system, you're going to have to move a bit slower. Yes, that's absolutely true.
It's not a physics podcast, but at the same time, I'm always curious about space. It's a thing that's fascinated me since I was a child. And a lot of people, they requested an episode with you and with the project that you do, which we're here to talk about, because you also happen to use Rust.
Yes, quite extensively, as a matter of fact. So for the solar sails, we have launched in January 2023, so right around the time when I joined the company, we've launched a satellite, a demonstration mission for this technology, the solar sails. And the onboard data handling system, our part of the satellite, is more or less completely written in Rust. So we have a few C libraries underneath the hood, but the main code and all of the supporting test equipment was written using Rust.
Now, isn't that extremely risky to use Rust for such a mission? You don't really have that many tries anyway. It's not like redeploying a backend or so.
Yes, this is one of the the great danger if you develop something for space. You get one shot with your satellite, and if you mess it up, it's not like you could just go up and try to reboot it. You know, you really have only one shot. But the mindset that we have at Gama is the mindset of the new space companies. So we try to move fast and fail fast. So we try a bunch of new things, and if we do fail, it's unfortunate, of course, but it's not a big deal. That's kind of how we do learn. And so what we wanted to do with this mission, it's a demonstration mission. So we wanted to demonstrate our technology, but we also wanted to try out new things. And so using Rust as the main driver for our onboard data handling system was one of these decisions that we wanted to try out to see if it's going to be usable for the future as well.
And before we talk about the onboard data handling system, what do you define as new space, and what are maybe other companies in that realm?
Yeah, so the main one that is probably known to everyone is SpaceX in that regard, and you can definitely see in their in the way they work that they like to fail fast as well. I mean, just look at the Starship launches. The development of this kind of a rocket is extremely difficult, but they're doing it very fast and they're failing very fast as well. I mean, many of these launches end with spectacular explosions, and so the mentality is, yeah, okay, we're going to have to spend a lot of resources, but we're going to learn a lot of it as well, you doing the failure. So yeah, that's just one way of moving forward versus in the past, the kind of old space, which is the big entities like NASA, they want to do it once and want to do it correctly. And I mean, this mindset is also very important if you're doing like deep space missions as well, where it takes a really long time to get to places. For example, as well, if you want to go to Mars, you kind of get one shot. And if you don't do it correctly, you're going to have to wait a couple, 10 or more years to get back.
Okay, it's a test mission. And yet it is foundational software that you're writing, because you might as well just use some of the more established, or like some of the more common languages like C, C++, or maybe even Ada for the test mission for Gama Alpha. But you chose Rust. Why?
So this mainly boils down to our software engineer at that time. So this was before I started working at the company. I didn't mention, but the Gama Space itself is only about 5 years old now. So it was founded in the 2020s. And we kind of move relatively fast, and the team only grows relatively so. So right now we're, I think, 21 people in the company. And at that point, when we launched Gama Alpha, it was more like 12. And most of our team is actually in mechanics, because as you can imagine, I mean, the folding and creation of the sail is its own topic. It's one of the main things that we do. And so we only had one electronics and embedded systems engineer, the one that was responsible for the creation of the onboard data handling system at the time, which is a colleague of mine called Chris. And his background was mainly in C++. And so he decided, but he knew that C++ was not well suited for, well, I mean, it was difficult to use to get a reliable piece of software for the space environments. And so when he looked into options and what other kind of languages to use, he decided that Rust would be a perfect fit for our case. He had a little bit of prior experiences in it as well. And so that's why we didn't choose Ada, for example.
And how did he evaluate Rust? I know that you were not there, but maybe you talked to them about it. Why did they choose it?
Yes. So basically, he did a trade-off of Rust versus other languages, and I mean, it came out clearly on top. The memory safety, just eradicating a whole bunch of errors that you can have with C and C++, is really critical for space applications. It's these kind of avoidable errors that can be caught before you deploy your code, that can just be denied by the compiler. And in general, the help that the compiler gives you compared to other languages in writing safe and good code, this was, I think, was the main driver. And of course, the ability to still go into the embedded systems level, still be real time, and be reliable.
How can I imagine day to day at Gama? Do you use any special software that us normal, let's say, earthly Rust developers don't use? Or would you say, no, it's mostly the same components, it's mostly the same code structure, it's the same CI/CD platform like any other project?
Yeah, actually, it's very, very similar. So in a bunch of companies, you would find setups with GitLab, for example, and so do we have it. We use a lot of crates that are, well, they're just out there, so for many people to use, like Zero Copy, for example, and other things, ProPRS for our debugging environment.
Nice.
It's a little bit more specific because we work with hardware. So in many just software companies, you have your code, you have unit tests, you have integration tests that you run on your CI, and that's that. We have to interface with actual real hardware. And so maybe one of the key differences is that we have a flat set for the Gama Alpha product. So for the Gama Alpha satellite, a flat set, I should say, is basically the electronics of the satellite unwrapped, laid out on a flat on a table. Hence the name flat set. And it's a one-to-one, pretty much a one-to-one copy of the actual hardware of the satellite. And we integrated it in our CI so that our tests, we have mainly integration tests, and they run on the actual hardware. And then we have probes attached to look at the actual output of the system and make sure that everything's all right.
If you want to learn Rust on a deeper level and really get your hands dirty with challenging problems while having fun and seeing your progress at the same time, I recommend checking out Codecrafters. I personally use it often to sharpen my skills and would recommend it to anyone who wants to become a better software engineer with Rust, or any other language for that matter. The challenges range from building your own shell to implementing Redis and SQLite, all the way to Kafka and DNS. This is perfect hands-on experience for backend engineers and systems programmers. And if you go to corrode.dev/codecrafters, you can try Codecrafters for free today and get 40% off when you upgrade to a paid plan. Head over to corrode.dev/codecrafters or click on the link in the show notes to get started today. It's kind of cool that you use ProPRS, especially because all of the embedded, or I call it embedded, but like all of the low-level projects that I know of use it to some extent. Was it a natural choice for you? Did you evaluate anything else? Is there even anything else in that space, or is ProPRS the de facto standard now?
Yeah, we did. It took us a while to get all of these systems up and running, and in the process of doing so, we did evaluate multiple things, but there was not a lot of choice for this sort of thing. We could have also just used regular C debuggers, as in just start a different process with the debugger and then interface with that. That was one of the other options that we looked at. I mean, that would basically have been the normal C approach, like just use a GDB, for example, as a debugger.
Yeah.
But the benefit of ProPRS was that, well, of course, it was written in Rust, and it allowed for a lot more fine-grained control of what we wanted to do with our integration tests. For example, we have a system to compile test Rust binaries and then upload them via ProPRS onto the actual hardware, and then look at the output and look for certain signals and to make sure that the test that this binary represents passes. So that was very easy to do in Rust and using ProPRS.
And how does that system look like? How does it work? What's the end-to-end development flow? So I'm guessing you develop code in your IDE. I'm not sure which IDE you use.
Yeah. So we use VS Code. And so if we want to develop a new feature or work on some code, the typical workflow would be, so you write your code, you push it onto a new branch, and as soon as you push, our CI starts, and it reserves a slot on the flat set. The interesting thing is that we also use the flat set for manual debugging. So we have kind of a little bit of a system where you can reserve a slot on the flat set. During that time, the CI can't run and has to wait. But if the CI is running, you have to wait for a bit until it's finished. And so we kind of have a little server, which unsurprisingly is also written in Rust. Yes, that kind of manages the access to the flat set.
And you wrote that yourself?
Yeah, we wrote it ourselves. I think it's been a while, but I think it uses Hyper as a web server. I think it's called Hyper, right? Yeah, and basically it manages access to it. At that time, so it has a web interface, and at that time we wanted to kind of get fancy, and I have a little bit of a background in Flutter development as well. So the web interface is based on Flutter, but the actual logic and the serving of the files is in Rust.
Oh, yes. Wow. That's a really cool project in and of itself, because I really wondered how would you test your hardware components? You kind of want to abstract that away. You don't want to unplug and plug it back in again. You kind of want to have a system for that. And I'm assuming that there's not much on the market, especially for flat sets like this. It's probably still an embedded setup, just like any other embedded setups, but the moment you go into the details here, you will find that you probably need a custom solution, right?
Exactly. So this is one of the unfortunate truths. If you do develop your own system, there's no one solution fits all kind of a thing. So we did try to find like generic solutions for embedded testing, and I don't know how it looks right now, but a couple of years ago, 2.5 years ago, there wasn't really a lot that helped you write actual tests for the embedded target and run them. So yes, this solution of the integration tests and the test suite itself is also a custom solution that we developed in Rust as well. So the whole integration test suite is also written in Rust and developed in-house.
But the integration tests are still in a tests folder, just like you would expect from any normal Rust project, right?
Yes, pretty much. So basically, it's a binary, that has all of the tests in it, and then we just upload this binary to the hardware and then let it run. And we look at the output via communication protocol. I think for that we use just UART, very common low-level communication protocol.
Now, earlier you mentioned correctness in a different context, but I think it fits in here as well, because couldn't you test a lot of the logic with unit tests? Or is it so that you kind of want to always test the inputs and outputs as well, because it's kind of a monolithic service?
Yeah, so we have some unit tests, and for smaller functionalities, we do use those to test. We kind of the theme that we have in our code is we have one big project, but it's split up in smaller crates. So the big kind of onboard data handling system software uses a lot of smaller crates that we also develop. And the smaller crates, they have unit tests for their functionality. But for the big onboard data handling system, it's harder to test these things because they're very much hardware specific. So, for example, if I want to test that our persistence works, so we are able to store data in some sort of flash memory, I can't just write a unit test for it because I need the actual hardware. I could try to emulate it somehow, but that's a bunch of extra work, and I'm not guaranteed that it is going to actually work on the hardware itself. So in an embedded environment, you kind of can't avoid doing integration tests because you need to test on the hardware. So you're just going to test the whole system as a whole. Yeah.
Well, when you say that you store files on flash, in a normal scenario, it wouldn't be a problem if the flash storage fails. You can't just, fix it because it's maybe right next to you, but it's harder to do in space. Do you have any failover for that sort of hardware failure? And if so, how do you test that?
Yeah. So in fact, all of our flash memory, first of all, it's a very specific chip usually that has some built-in error detection and correction. So on a hardware level, we are protected against it. But on top of that, for specific parts of code that is stored on this flash, because that's the important thing. Code needs to be stored somewhere. And so if that code gets corrupted, you're going to be in big trouble. So one of the steps that we do in our bootloaders is that we check this code for error and for errors. Yes, for example, for bit flips. In space, you have radiation, and so just random bits in your data and in your code in that instance can just randomly flit, which can mess up the entire code flow. So we have steps, we have code written to verify that the stored code that we have in our flash memory is correct and that can potentially even recover from errors. So there's something called a Hamming code, which means you basically reserve some extra space for redundant bits, and you can use those bits later to detect and to recover from flipped bits. And this kind of code, we have an integration test that uses PropRS to manually write into the flash, into memory even, and to flip some bits. And then we'll let it boot, see that it handles these kind of corruptions that we introduced correctly and fixes itself, yes.
And that's also a custom solution.
Yes, I mean, this is one of the tests that we run during our integration tests. So yes, the integration test suite has a component that allows it to write into this flash memory, and that is developed by us, and that's a custom solution indeed.
Let's talk a little bit about your background, where you came from, what your other strong languages were, and how you got onboarded on the project and your first experiences with the code base. A lot of people might be curious about, exactly this process of working for quote unquote a space company.
So during my studies, when I joined a lot of projects that do things in space. So for example, one of the cool things that we did back then was something called Bexus and Rexus, which is a European project for students that allow you to do some sort of project, some sort of scientific mission on a small suborbital rocket or weather balloon that they launch from Sweden. And so that's kind of where I got exposed to my first real space mission experience using those projects. And we used a bunch of different languages there, though mainly C and Python. And I must admit, before I joined Gama and in my university days, I have never heard of or used Rust. So I'm kind of a late joiner in that regard. But after finishing my studies, I joined Gama then in January 2023. And that's the point when I started to learn about Rust and when I kind of fell in love with it because of the security guarantees that it takes, that it gives you. You mentioned earlier that all of the stuff that we have talked before must have been in place before. And that's actually not the case. This is one of the reasons I got onboarded, because at that time it was literally just Chris responsible for the software. And so we really needed more support in the electronics and in the software department, the embedded software department. And so that's where I came in. Although I couldn't directly start working on the onboard data handling system. Well, I did some small contributions here and there. But when I started, I got assigned to a kind of a side project. So you have to imagine the satellite has just launched a few days ago. I come into the company, I get used to everyone, like everything, meet everyone. And then, okay, we have kind of a validation of our satellite. We want to do a zero-G flight. So that is a flight where the plane does a parabol. So it goes up and then it flies in a way so that you cancel out gravity. So for a few seconds, like 30 seconds, you are weightless. And we wanted to use that and develop a system to have a small-scale solar sail deployed and to see how it behaves in zero-G, because they had simulations at the time, but there was no practical experience. And so we wanted to see if our simulations actually match what we see in real life. And so I got assigned to build this specific project and the code for it. And of course, because we were using Rust, this was also done in Rust. So it was kind of a relative simple thing. We just had 3 motors and we were controlling a disk inside of a box. And on that disk, so we were able to spin the disk and then release something that released our small scale sail. And the main part of this was just to do this control kind of account for vibrations of the plane because those kind of disturb the data, and then record the data, of course. There was a lot of data coming in because we wanted to record as much as possible from this experience. We had cameras that captured the entire thing, but we also had various sensors, accelerators, and stuff like that. So that was kind of my first my foot into the company, and that's kind of also still what we do today. If somebody else joins the company, they're going to have to get used to the way we work around here. They're going to have to get used to Rust potentially. And so they usually get a small project on the side where they can work on. It's still important to us, of course. And then they kind of join the main force like that. And we have a bunch of back and forth where because you're learning, you're learning the way of how to write code, not only for Rust, but also for space. There's a bunch of things that we how-tos that we have in the company that we've gathered over the years on how to write Rust safely as possible. Because unfortunately, it's still possible to screw up in Rust.
Is it?
Yes. So yeah, one of the main things in the beginning, I thought, it's so cool. There's like I can't get wrong with this. If my code compiles, it's perfect, and it's true in most of the cases. But some logic bugs can still sneak in. Mostly if you don't write your code in a way that prevents them, because that's one of the cool things about Rust and what we use extensively here as well. If you write your code using the strong type guarantees, you can make it so that any invariants that need to hold true, so any preconditions that your code has and that need to be true for it to work correctly, you can express that in the type system. Well, maybe not all of them, but most of them. And so, for example, we use that extensively for configuration. We have code that can only run once the hardware is initialized correctly. And so we pass around zero-sized tokens, types that can only get created in one place in the system, and that's after initialization of that specific hardware. And so we use, for example, this sort of a token in other places to prove, yes, this code will only ever run after initializing that specific hardware.
Couldn't you also use a type state pattern for that?
Well, if you do that type state pattern, you kind of make code dependent. You encapsulate the code. Not encapsulate. You make it dependent on each other a lot more, I feel like. So instead of writing a huge state machine, basically, like that, you can write your code more freely, just at any given structure that you want, just passing around these types as keys.
Yeah, I never heard about that types with keys pattern, the token pattern that you described. Is that a thing that you invented, or does it come from any other project?
Well, it's definitely used in the embedded world a lot. Maybe not in the same kind of way, but we've got the idea from crates like Embassy, and actually various hardware abstraction layer crates, that if you, in the beginning, they give you one struct that contains all of the peripherals, but it's just zero-sized types for these peripherals. And the idea behind that is that you can then, when you want to use one of these peripherals, you have to consume that type. And that prevents you from using the same peripheral twice. For example, pins. If you think about a microcontroller, it has pins that you can toggle on or off. And if you decided at one point, yes, okay, I'm going to use this pin to talk to a motor, for example. And then later you think, okay, wait, I have another use for a pin. Maybe, I want to toggle an LED or something. Let me see. Maybe pin 1 is still available. I'm going to try to use it. No, I've already used this before. And Rust tells you this because you moved the type, you moved the variable into the function that used it. And so you can't use it later. And so that's kind of the same idea. You have a token for each peripheral, for each pin, that you can only use once. And this is one of the things I really love about Rust. it's the ability to detect these kind of configuration errors at compile time. I mean, the compiler literally prevents you from writing code that is wrongly configured. That would be valid code from a processor perspective. I mean, it's okay if you use the same pin for two different things. You can write to the registers and it's not going to care. But the end result is that the pin is not going to do what you want because you're using it for two things at the same time. And by expressing this notion of, only one part of your program can use this specific thing via a token, the compiler can ensure that this, in fact, is the case.
And now I understand part about loosely coupled components as well, because I'm not sure, but I guess Embassy used the type state pattern and a lot of generics for the pins before. I'm not sure if they dialed it down a bit or dialed it back, because you sometimes want to repurpose pins, and if you set up your system once, it's not as flexible as if you were to be able to, change that dynamically, sort of. And at the same time, you just use the normal ownership rules in Rust to enforce the same behavior. So you can still encode it in the type system without really having a lot of overhead and a lot of complexity on the type system level.
Exactly. Yes, as I said, we use this in a bunch of places. Also, for example, for wrapping C libraries, it's kind of an interesting thing. During our Gama Alpha project, we used a communication protocol called CSP. And unfortunately, at the time, there was no pure Rust implementation of it. So we had no choice but to wrap, either implement the whole thing ourselves, but that would have taken quite a bit of time, which we didn't have, or to wrap the C library. And the C library has a bunch of invariants when you use it. One of them is you have to call a function called CSP init before you do anything else. And so this kind of a thing, once again, we have a zero-size struct in Rust called CSP. It has an init function, and it is the only place where you can get an instance of this CSP struct. And then the CSP struct allows you to call other functions on itself. But you need a self, so you need an instance of the struct. And so that proves that you have initialized the CSP, the underlying C library.
Because that's sort of the only place where you can get that token from.
There's only one place to get this token, and in that place we initialize the library just before. So it's kind of a way of you have one place in your code where you know about these invariants, and you only need to to express these invariants at that place. So for example, if I have function of this library and I know it needs to be initialized before, all I need to do is I need to take a reference to this token. And that guarantees me, yes, the library has to be initialized. And so as a user of this library, which is also us, but sometimes you can forget. Maybe you forget that you have to initialize the library before, or you're just, you're moving one line of code few lines up by accident before the initialization, because you think, this might be more efficient that way, or something like that. You forget about these invariants much too easy. But by encoding them into the type system and by encoding them into the function signatures, we can still enforce it, and we can let the compiler help us in not forgetting about it.
That's pretty impressive. At the risk of going a bit meta here, how do you come up with these patterns? Do you find them online in certain other crates, or do you think really hard about those problems and then start to encode those invariants? It's not really discoverable.
Yeah. So I think the way we discover them is by failing, by writing code that is invalid, and where we then introduce certain bugs, and then later discovering, we need to prevent us from ever writing that code again. And so, for example, with the case of the library, it was literally the case that we called the function before we initialized it. And so that's how we got the idea of, we need to prevent that. How do we prevent that? Let's use this token system in Rust.
Do you write down those correctness guidelines? somewhere?
Well, we do have a bunch of rules like that, but the point is you only have to write them in code, right? So once you corrected that mistake, once you made sure via the type system that it's impossible to use a function in an incorrect state, you don't have to write anything anymore because the compiler will enforce it.
Mm-hmm. Well, I guess you review a lot of Rust code nowadays, a lot of Rust code that should or cannot fail. How do you review Rust code for correctness? What do you look out for? What are some common patterns that you found useful here?
Yeah, for reviewing, I like to think about all possible states that a certain Rust code can be in and all possible inputs. It's kind of like fuzzing, where you but manually fuzzing. We like to split up our code and our merge request into small chunks, and so it's relatively easy usually for us to think about all the possible inputs and what can go wrong. And then I like to make sure that we use the type system to its full extent and to encode any preconditions, as I said, into these types. It's kind of like if you have a precondition for using a value that can't be zero, in Rust, you have the non-zero type. Right? So Rust itself uses a lot of these types for preconditions as well. Same with the C string, a string that has to be zero, null byte terminated. So Rust itself gives us a lot of these ideas as well. And so when I examine code, I'm just trying to think of all of these different invariants that need to hold true for a specific code. I'm trying to find them out and make sure that they're expressed as much as possible.
Are you a friend of debug assertions?
Yes. Well, I mean, we use them extensively as well, but only in places where we can't guarantee something just with the type system. I mean, there's always certain things that you can't guarantee at compile time, especially if you're interacting with hardware, right? Some of these things you just can't do with just the type system.
For example?
Some of the runtime state that can't be known at compile time, we, for example, have our own heap. And so the idea of a heap is that you have a bunch of memory available and you at runtime allocate things out of that heap as needed. And you can never kind of really be sure how much you allocate just from looking at your code, because it depends on timing. It depends on when certain pieces of code need a certain amount of memories. And so for those kind of invariants, so if we request a piece of memory but we don't have any more, for example, like this, there has to be still debug assertions. And in fact, Rust itself brings a lot of debug assertions as well, right? Every time you access an array, for example, or a slice, you have debug assertions that make sure that you don't go over any of the limits in memory. And that's one of the strong systems of Rust as well, right? That's the memory safety. All of these checks at runtime as well. Of course, you can disable them, but this is, for us, it's a trade-off of size versus the security. And for the Gama Alpha project, at least, we were able to leave debug assertions on. Because that's another part of the space industry. Usually you work with hardware that is not like your modern laptops and computers where you have basically unlimited memory and space. No, our programs need to fit in tiny flash memories. And so removing debug assertions can be one of the ways where you can have more actual code, but with a smaller size.
And by tiny, you mean how large?
Think like a couple 100 kilobytes.
Oh, wow.
Yeah, it kind of depends. I mean, for the Alpha satellite, we had, I think, so the processor itself had an integrated flash memory of 256 kilobytes. And then we had an external chip with, I think, an additional 1 megabyte of flash, if I'm not mistaken. So not a lot of space, and some of the space you need for data as well, because Yeah, you talked about this in a previous episode. You talked with, I think, cubesat, a provider of ground stations. So you might be familiar already, but a satellite doesn't have a direct communication to the ground all of the time. We also need to store data on the satellite itself before we can pass it down to the ground stations.
Okay. It turns out there's not a lot of space in space. You work on tiny hardware. And shout out to Vegard as well. It was an amazing episode too. Now, Rust has fallible allocations for vectors nowadays, but I'm guessing that you even want to avoid allocations in the first place, especially the dynamic allocations.
Yes.
And Oxide, for example, has a scheduler called Hubris. And Steve, please correct me if I'm wrong here, but Steve Klapnick, that is. I think what they did was they used static allocation, static memory, and every payload that they run on that scheduler has a fixed size known at compile time, which allows you to have predictable allocations. Do you use that pattern as well, if you can? So having a fixed struct and knowing that only this struct will need to be allocated, quote unquote, on the stack?
Yes, as much as possible. So whenever we can use it, we try to avoid the allocations and just use stack variables. Or we have our own stack allocated statically and use elements out of that. But sometimes it's just not possible to know at compile time what kind of how much memory you need to use. For example, think about the telecommand stack. So for the Alpha satellite, we were able to send telecommands to it. And on the satellite itself, you don't know how many telecommands will come in at a given time and how long it takes for each telecommand to be worked on. And so we had a queue of telecommands. And this queue, of course, has an upper limit, but the memory out of it was kind of heap allocated, because it had an upper limit, but it was taken out of a big slab. Mm-hmm. But in all other cases where we really try to avoid using the heap. I mean, that's the no SCD environment for you. You don't get a heap for free. So you need to provide your own heap if you need it. And so you're very, very specific about the places that you need a heap, and you try to avoid it in all other cases. One thing that can help with that a lot is a crate called zero copy, for example. In our telecommand and telemetry system, we use it very extensively. So the way it works is you define your structs, the data that you want to be able to send, and we use zero copy to convert them or let them be converted safely into bytes and from bytes without the use of an extra buffer, without the use of an extra allocation. Just the same amount of memory. It's basically a safer transmute. And so, because we need to send the data as bytes, obviously. So we need to do this conversion to and from bytes. And zero copy is a great help for that sort of work.
If I understand correctly, that means you don't initialize the struct. You have a view into this byte block, in this block of bytes, and zero copy kind of makes that safe for you.
Yes, in a way. So there's two ways of using it. First of all, the easy way is you already have a struct and you want to convert it into bytes and send those bytes over the network. Zero copy helps you with that. But then the other way around, you receive a bunch of bytes and then you want to pass these bytes as a struct. And zero copy makes this conversion from just a view of the bytes into a reference to the actual struct possible and safe, by making sure that there's no invariance that can't be upheld. Or in newer versions, at the time they didn't have that, but in newer versions you have a try variant of all of their functions, which allows to test for certain invariants. For example, if you want to receive a Boolean can either be 1 or 0. But a byte can be 0 to 255, right? So you have a bunch more values that normally shouldn't be allowed. And these need to be verified. And that's also one of the critical things. In C, I saw a bunch of code where you just convert from your bytes into integers, and then you use those integers somewhere else. And it's very easy to mess up with just not validating your input enough. And especially if you accept input over satellite connection, there's a bunch of bits that can flip. There's a bunch of stuff that can just go wrong. And so you really need to be sure to pass it correctly. And once again, we can use Rust's type system by making the constructors to all of these payload structs private and letting it just take bytes and doing all of these validation in this new function in the constructor and returning an option of ourself. And so if or result of ourself. And so if any of the preconditions, they're just local, they're right next to the struct. So it's easy to verify that all of the preconditions that we need when converting from a byte string are checked for. And then afterwards, you're sure if you have the struct, its data is validated.
Well, that's really nice. It's a nice example of making illegal state impossible to represent and parsing instead of validating. That's kind of cool. You said that zero copy is a bit like a safe transmute. Would that mean you can ditch transmute altogether and always use zero copy, or are there any cases where zero copy just doesn't provide a safe interface?
Actually, we have no instances of transmute, and we kind of, it's on the list of things that we really try to avoid. And so far, we have not come across of a use case that is not covered by zero copy. So, of course, sometimes we have to convert between different types in Rust, and we use as for that. But those are safer conversions than just using transmute. And the fact that the type system guarantees no just random conversion between different types is really helpful to reason about these invariants in your code. So for example, just think about in C, I can create any struct at any point in any time. In Rust, you need unsafe to do that. And it's a big kind of flag. If you see unsafe in the code, it helps you during the review, because you need to, when you use unsafe, you always need to prove, at least with a comment, that certain invariants are holding up. And that makes it very easy to prove that your code can be safe, even if you're using unsafe. So unfortunately, we still have C libraries underneath, which are all unsafe. I mean, it's C code, so there's no help from the Rust compiler there. And so interfacing with those does require unsafe boundaries, or unsafe blocks. But when we write our wrapper functions for these functions in the C libraries, we make sure that all of the unsafe preconditions that needs to be met for this library to be called are met. And one of the examples is, as I said, the CSP library, where we make sure that it's initialized before we use any of the functions.
Okay, you try to minimize unsafe code. Do you also try to minimize unwraps? Are there any better patterns that you use?
Yeah. So unwraps, direct unwraps are also somewhat forbidden in our code. The best that we can do are expects, where you provide a message and a reasoning of why this certain thing can never fail. And there's still a few pain points in Rust with this, where you do need to unwrap certain things. For example, think about creating a non-zero value. You can do this unwrapping or this expecting in const code, which is very nice. So you can make it a compile time error. Yet still, it's unfortunate that certain things can't be expressed as you want them and need to be unwrapped. But we are constantly fighting that. For example, in cases where we do need a buffer for certain things, and we know beforehand that we need a certain size, you can add certain trade bounds using the unstable const generic features that prevent you from needing to use unwrap, and then just giving you the actual value that you want without using a result or an option. And that's only possible because you let the compiler validate these preconditions at compile time.
In my mind, you learned Rust in hardcore mode. It's in the space industry as a startup, straight out of university with a Python background, and then also needing to ship features really early on, working there. What would you recommend others to do on how to learn Rust effectively, learn it quickly, learn it well? How would you flatten the learning curve?
Flattening the learning curve, that's a big kind of issue in Rust, I would say, compared to Python, for example. I think just trying things out and learning by example is the easiest way to do. Unfortunately, I don't have a fix, like a solution for everyone. But the thing is, you struggling a bit with the compiler is a bit frustrating in the beginning, but it's a very valuable learning experience. So if you start out using Rust and you're having trouble with lifetimes, with borrowing, whatever, it is the compiler trying to help you. And once you realize this, once you understand that the structures and the ways you did it before are a little bit flawed in regard, once you understand this, it does help you. Unfortunately, it is a hard pill to swallow sometimes, but it's very useful. I myself, after learning Rust this way, have come back to various Python projects and found out that code that I thought was perfectly fine, that I wrote many years ago, actually had subtle problems that could occur under some circumstances. Not all of the time, but sometimes. And so these, for example, if you have multiple threads and you access certain variables over multiple threads in Python, there's very little help for you to avoid accessing a variable at the same time. In fact, there's none. You need to do that yourself. And in Rust, you can let the compiler help you with that. And initially, of course, it's harder because you need to prove that you're doing these things in a safe way. But it does help you to avoid certain logic bugs that would be easy to make otherwise.
So see the compiler as an ally.
Exactly.
Try to take a step back and take your ego out. Look at what the compiler is trying to tell you, and try to improve.
Yes, that's one of the very valuable lessons. Rust is amazing, and one of the main things is the compiler helping you so much. And once you understand that it's not you versus the compiler, but it's you and the compiler versus bugs, then you have a much easier time moving forward, even if it takes a bit of time to get there, admittedly.
100% sure that there are people out there who would like to send in a job application right away or would like to work in that space. What are some next projects for Gama, things that the team will be working on? Maybe also on the Rust side, what are the next challenges? What's coming up?
Yeah. So, well, if people are interested in joining Gamas, we do have some job applications usually on our website, gamaspace.com. So that's where people can find us. So right now, the Gama Alpha satellite actually the work on it has been finished for more than a year. And we are moving forward with a different kind of sail, a so-called drag sail, which is a way of deorbiting a satellite. So bringing a satellite into lower atmosphere where it can burn up so that it doesn't take up any space anymore in space. Because even though space is vast, the space around Earth is not. And yes, so there's a need for cleaning that up.
Does that mean Rust does not have a garbage collector, but you use it as a garbage collector?
In a way, I guess. Although I must say, so for this product that we are developing there, and actually that has already been sold in Q1 this year, we decided that we needed a lot and like a real lot of reliability. So this is one of the main drivers of why you need to have this kind of a system. Your satellite is 5 years or 10 years in space. There's a lot of radiation, there's a lot of events, and it can fail at any moment. And so our component needs to be as reliable as possible. And for that, we decided to have actually no code whatsoever on this product itself. But that doesn't mean that Rust isn't involved at all. In fact, all of our test equipment, we have a dedicated little microcontroller and setup for testing our equipment, is still 100% written in Rust, or as much as possible. And so, but the actual drag cell that we're developing right now is purely based in electronics. The version that we're doing right now. In the future, so the version we're doing right now is for small satellites, but in the future, the next big project will likely be a larger version of it, using a lot more complicated hardware, which will require, once again, software. And for that, we're going to be able to reuse most of the codes that we've written for the Alpha satellites. So all of the software stack, the different bootloaders that we have, the onboard data handling system, most of it can be rewritten and so it can be repurposed, basically. The hardware is going to change a bit, but because we split up everything into multiple crates, we have a crate specifically for drivers of the hardware. So that is the thing that mostly is going to change. But other logic on top of that can stay the same. In fact, that's one of the reasons why we split up the organization of our code into so many crates. We have, I think, 59 crates in total in our internal crate registry. Not all of them are directly related to the onboard data handling system. Some of them are also for the test equipment on ground. But splitting up the codes into well-defined little bits allows us to reuse most of them in space. It was kind of the idea from the very beginning.
Traditionally, the final question is, what's your message to the Rust community?
Well, I think that Rust itself is an amazing tool, and the Rust community is doing an amazing job in providing it, in caring for it, in also providing no STD crates. That's very important for our purpose. And I think for those of you in the Rust community that provide these crates, let's try to work on letting the compiler help us as much as possible. So leaning into constraints, leaning into the ability of having these marker types, because anything that we can handle at compile time is something that doesn't fail at runtime. And failing at runtime in a mission critical environment like space is never a good idea. So if we can, let's try to work towards letting the compiler help us as much as possible.
Sebastian, thanks a bunch for taking the time.
Thank you very much.
And with that, we're closing out Season 5 of Rust in Production. Thanks to all our amazing guests and thanks to you for listening. A special shout out to Simon Brüggen, who's been editing the show since episode 1. We'll be back soon with more production stories. In the meantime, if you're thinking about migrating to Rust, we'd love to help. Head over to corrode.dev to learn more. And hey, if you enjoyed the show, the best way to support us is to leave a review on your favorite podcast platform or share an episode with a colleague or friend. It really makes a difference. Have a nice break. We'll see you in Season 6. And thanks for listening to Rust in Production.